Welcome. All right, so now we're going to look at some problems with definite integral involving absolute value. So for absolute value, you do have to break it into a piecewise function. You'll rewrite it as a piecewise function. As a reminder, when you're rewriting a function, an absolute value function into a piecewise function, you have two parts. You have the positive part, which is just what you see in the absolute value bars. And then the negative, all terms change to the opposite. So it's like you're multiplying every term by a -1. And for the breaking point, you simply set the absolute value expression equal to 0. So here's our first example. We have the integral from 0 to 2 of the absolute value of 2x minus 1 dx. All right, so we're going to rewrite that because it's absolute value. For the positive piece, that's just 2x minus 1. No changes whatsoever. For the negative, that we just distribute a negative to the 2x minus 1, so that's negative 2x plus 1. And the breaking point, you just simply set 2x minus 1 equal to 0, so x would be 1/2. All right, so this absolute value function rewritten is 2x minus 1 if x is greater than or equal to 1/2, and negative 2x plus 1 if x is less than 1/2. All right, there's our function. All right, so that's what we're going to integrate. So we're going to split this, and we're going to split it at that 1/2. So we have from 0 to 1/2. Negative 2x plus 1 dx. And then, so the negatives is for the less than 1/2. So from the lower limit 0 to the breaking point. And then plus from 1/2 to 2, 2x minus 1 dx. So we simply split it at the breaking point, and now we're just going to integrate. All right, so if we integrate, this would be negative 2x squared divided by 2 plus x. We're just undoing the power rule here. And that's from 1/2 to 0 to 1/2. And then the other part would be 2x squared divided by 2 minus x. And that would be from 1/2 to 2. Let's reduce. So this is negative x squared plus x from 0 to 1/2 plus x squared minus x from 1/2 to 2. Now we evaluate. So plug in the upper minus the lower. So negative 1/2, and that negative is not being squared, plus 1/2, and all of that is, we're going to subtract negative 0 squared plus 0. I think that's 0. And then the other part, plus. So this is one piece. Then we have the other piece. And that would be 2 squared minus 2. And from that, we're going to subtract 1/2 squared minus 1/2. I'm starting to write downhill again. Kind of a reach there. If I stand up, though, and block the board, you can't read anything. So I try not to go downhill so much, but I can see it in the screen. I'm going downhill already. All right, so negative 1/2 squared, that would be negative 1/4 plus 1/2. This is just minus 0. And then plus 4 minus 2, that's going to be 2 minus, and then we've got, this is a 1, that's a terrible looking 1. 1/2 squared. There we go. That would be minus 1, it would be 1/4. So minus 1/4 minus 1/2. Let's simplify that. So negative 1/4 plus 1/2, that's a 4th. Minus a 0, don't need that. Plus 2 minus, so this would be 1/4 minus 1/2. That would be a negative 1/4. So that's just going to be a plus. So we've got 1/4 plus 2 plus 1/4. That's 2.5 or 5/2. All right, and that's all we need for that problem. I'm going to pause, and then we'll do a second problem. All right? All right, so here we are, our second problem. I've written a little bit of it for you so that go maybe a little faster. And I just wrote the easy parts, the rewriting. So we have the absolute value, the integral of the absolute value of 4x minus 10 dx evaluated from 1 to 5. So we see absolute value bars right away, rewrite. All right, so the positive, nothing changes, 4x minus 10. Negative, just distribute a negative. So that makes it negative 4x plus 10. The breaking point, set 4x minus 10 equal to 0. Right, so x is 10/4 or 5 halves. So this absolute value function is the same as this piecewise function, 4x minus 10, if x is greater than or equal to 5 halves, and negative 4x plus 10 if x is less than 5 halves. So we're splitting the integral at 5 halves. All right, so our rewritten integral is the integral from 1 to 5 halves of negative 4x plus 10 dx plus the integral from 5 halves to 5 of 4x minus 10 dx. All right, so now that we've split it, that's the only thing that's different for absolute value. We split it, and the upper for the first piece is the lower for the second piece. All right, and now we integrate. So this would be negative 4x squared divided by 2 plus 10x. We'll evaluate that from 1 to 5 halves plus 4x squared divided by 2 minus 10x. And we'll evaluate that from 5 halves to 5. All right, so now let's simplify that. That would be negative 2x squared plus 10x evaluated from 1 to 5 halves, and then plus 2x, neither 2x squared minus 10x, and that would be evaluated from 5 halves to 5. Okay? All right, so now that we've got it rewritten, actually, neaten that up a little bit. Now that we've got it rewritten, let's evaluate. So we have negative 2 times 5 halves squared, and then plus, and put parentheses on that, plus 10 times 5 halves. And then from that, we're going to subtract the negative 2 times 1 squared plus 10 times 1. I need to learn to write smaller, I think. And then we're adding the second piece, which is going to go down another row, apparently. So we have 2 times 5 squared minus 10 times 5. Here, you know what? That's just so squished in there. Let's just put a big old plus here. I'll move the whole second part to the bottom row here. So then that would be 2 times 5 squared minus 10 times 5. And from that, we're going to subtract 2 times 5 halves squared minus 10 times 5 halves. Yeah. So all of this is a lot of evaluating. So 5 halves squared, that would be 25/4 times negative 2. That's going to be negative 25 halves. Okay. And then 10 times 5 halves, we could reduce that, right? 50 halves, 25, however you look at it, right? 25. And then minus, we've got negative 2 plus 10 plus, this would be 5 squared times 2. That would be 50 minus 50. Whoop, boy, there that goes. That doesn't happen too often. And then minus, let's see if we can squeeze that in. Actually, I'm going to just erase this and make that a little smaller. And then, so that would be 5 halves squared would be 25/4 times 2 would be 25 halves. And then minus 50 halves, that would be minus 20, minus 25. All right, so now let's simplify that. All right, so negative, let's just combine in the parentheses and distribute negatives. So this is negative 25 halves plus 25. I'm just going to leave it like that for right now. And this would be minus, so this would be 8, so that'd be minus 8. And that's 0. And then this would be minus 25 halves. And we distribute the negative plus 25. All right, so now let's combine some like terms here. 25 plus 25, right? That's going to be 50. And then minus 8. So let's just do 50 minus 8, that's 42. And then negative 25 halves minus a 25 halves, that would be negative 50 halves. So that's minus 25, and this is 17. And that's our correct answer there. So really, the integration part took this much, plugging and evaluating took this much. So that's usually the hardest part on this. Right? So the next thing we're going to look at is continuity. Right? And I'm going to pause the tape and I'm going to bring up some continuity problems. And that'll be the end of this video. All right, so here are our continuity problems. If the given integral satisfies the hypothesis of part 1 of the FTC, then compute. Otherwise, explain why FTC cannot be used. So let's look at the first one. Okay, well, this is a continuous function on the interval of, well, first of all, do you recognize who that is, right? So if it helps, we could factor out the 8, right? So the integral of a constant times a function is the same as the constant times the integral. We can factor that 8 out, right? So this would be the same as 8 times the integral from 1 to square root of 2 of 1 over 1 plus x squared. All right, so now this is not a power rule, and this is not natural log, right? Because if this was natural log, the derivative would be up in the numerator. But as we'll see in some examples later on in other videos. But what this is, do you remember? That's the derivative for arctan, right? The derivative of arctan, right? So when we take the derivative of arctan of x, we get 1 over 1 plus x squared. Right? So that's arctans. Now, this will be, we can integrate this so long as we're continuous on this interval, because this is a definite integral here. And it goes from 1 to the square root of 2. Now, if you remember, arctan is defined from negative pi halves to pi halves. Square root of 2 is approximately 1.4. And they're both positive. So we're definitely in this first quadrant, so long as we're under the square, pi divided by 2. There we go. Well, pi is 3.14, et cetera, right? And half of that would be a little bit more than 1.5. So the square root of 2, so both 1 and the square root of 2 are between this negative pi halves. They're greater than negative pi halves, because they're positive, right? And they are both are less than pi halves, right? So no problems there, right? Tangent's not going to be defined at pi halves, right? It has a vertical asymptote. Excuse me, arctan is not going to be defined at pi halves. It has a vertical asymptote, right? So we're okay. All right, so let's evaluate. I'm going to put that up there so we can evaluate afterwards. So now let's integrate and then we'll evaluate. So this would be 8 times arctan of x, and we're evaluating that from the 1 to the square root of 2. All right, so we can plug so when we're looking at 1, we're looking at where is tangent 1 and where is tangent square root of 2. Well, one of these is a lot nicer than the other. Right, so this would be 8 times arctan of the square root of 2 minus 8. You know what? Let's distribute the 8 at the end. Or you know what? We'll distribute it now. Because we can simplify a little bit, but not a whole lot. 8 times arctan of 1. The one that we can figure out easily is arctan of 1. In other words, where is tangent 1? Right? Well, tangent is 1 when the opposite and the adjacent side are both the same. They're both 1. Well, when is that going to occur? Right? Well, that's going to occur in the isosceles right triangle, the 45, 45, 90, or the pi fourths, pi half. So this here is pi fourths. Right? So we can replace this one anyway with pi fourths. So then we would have 8 arctan square root of 2, and then minus, and that would be 8 times pi fourths. So as nice as this gets would be 8 arctan of square root of 2 minus 2 pi. And you might think, why didn't I evaluate arctan of square root of 2? Well, it's not a very pretty number. It's certainly not an exact number. It's a decimal approximation. We may as well just leave it like this, right? The exact answer. Let's try the next one. All right, so is it continuous? Yes, it is, right? X just can't equal 0. Right, so no problems there. All right, so, and 0 is not on that interval. All right, so let's just evaluate. Now to evaluate, we're going to have to rewrite this, right? Because there's no undoing the quotient rule. Right? I can't undo this unless I rewrite it with a negative exponent. So I'm just going to rewrite this as the integral from 1 to 2 of 4x to the negative 3 dx. And now we can easily integrate that. Right? And now it is just with the power rule, undoing the power rule. So that's going to be 4x. Now negative 3 plus 1 would be negative 2 divided by negative 2. Right? And then we're evaluating that from 1 to 2. Let's simplify that. So that would be negative 2x to the negative 2 power. Let's just make it negative 2 over x squared. Right? That looks a little nicer, and we're evaluating that from 2 to 1. So that's going to be negative 2 divided by 2 squared minus negative 2 divided by 1 squared. So that's negative 2 divided by 4. So that's going to be negative 1/2. And this minus a negative, that's going to make that a plus. That's just going to be plus 2. So our answer is 3/2. The next two are going to be pretty quick. Notice this is the exact same problem, the integral of 4 over x cubed from 0 to 2. But hey, I can't plug in a 0. X can't equal 0. All right, so here the fundamental theorem of calculus does not apply. Because the integral is not continuous on the interval. How about the other one? All right, well, I got x minus 2 in the denominator. If x minus 2 equals 0, x can't equal 2. Well, 2 is right in that interval, right? 2 is in the middle of 0 to 3. So again, Same thing. The fundamental theorem does not apply because the integral is not continuous on the interval. So you cannot integrate and evaluate. You can't integrate and evaluate at all if you do not have a continuous function on the interval. All right? So there are some problems with the fundamental theorem of calculus and continuity. Thanks for joining me, and that is the end of this video.